Okay, in this video we're going to learn how to find the greatest common divisor, also known as the GCD, of two numbers. Actually, it's known by another name. As I say at the very beginning, the greatest common divisor, the G stands for greatest, C common, D divisor. It's also known as the GCF, for greatest common factor. They're identical. There is no difference between them. So the greatest common divisor of two numbers, A and B, and these numbers are always going to be positive whole numbers for our class, is written the GCD, parentheses AB, and A and B will be two numbers given to you, is the greatest factor which evenly divides both A and B. So here's our first example. The GCD of 4 and 6 is equal to 2. Since 2 evenly divides both 4 divided by 2 is 2, and 6 divided by 2 is 3. And it's the largest or the greatest number for which this is so. So literally it's just showing you that this answer satisfies the definition. So this tutorial is about how to find the GCD. So here are some easy ways to find the GCD that don't always work, but when they do, they're usually easy. It's usually easier to use one of these methods. So given two numbers, A and B, to find the GCD, keep these common facts in mind, and I'm going to go over each one of those. If you can use any of these facts, it makes finding the GCD easier. So the first fact is that the GCD of two numbers, A and B, is always greater than or equal to 1, but less than or equal to the smallest of the two numbers, A and B. So we see this in the above example. I'm talking about this example right here. Since 2 is the GCD of 4 and 6, and 2 is greater than 1, but less than or equal to 4, which is the smaller of the two numbers. So that's always something to remember. The GCD is always greater than or equal to 1. Sometimes it is equal to 1, but less than or equal to the smallest of the two numbers. So if you were to be given, for example, down here, we're going to find the GCD of these 6 examples. If you were to say the GCD of 3 and 9 is 12, then something's wrong, because the GCD is less than or equal to 3, but greater than or equal to 1. So that was fact 1. Use that. Fact 2. If the smaller of the two numbers, A and B, it's customary that these be italicized, so I'm going to italicize them right now, evenly divides the larger of the two, then the GCD of A and B is just equal to A. So here's a specific example. The GCD of 4 and 20 is equal to 4, because 4 evenly divides 20. 20 divided by 4 has no remainder. It's 5 with 0 remainder. So remember, we already knew that whatever the GCD was between 4 and 20, it was going to be greater than or equal to 1, but less than or equal to 4. In this case, it's equal to 4, because 4 evenly divides 20. So here's the next thing. We'll talk more about these in class later on in a future section. But a prime number is a number evenly divisible only by 1 in itself. And when I'm talking about numbers in this context for this lecture, I'm always talking about positive whole numbers. For example, the following numbers are all prime: 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Indeed, those are all of the prime numbers between 1 and 30. There's an infinite number of those that's been known since ancient time, but we'll just look at the first few. So here's the third big hint. If one of the numbers, A or B, is a prime number, and condition 2, this one right here, is false, then the GCD of those two numbers is 1. So for example, the GCD of 5 and 21 is equal to 1. Notice 5 is prime, but 5 does not evenly divide 20. That's condition 2. So condition 2 is false. So it's equal to 1. But the GCD of 5 and 25 is equal to 5. Why? Because condition 2 is true. 5 evenly divides 25. So it's equal to the smaller of the two. So we're going to use these facts to find the following. Now, I'm going to tell you right now, really what I've given you is this is kind of, number 1 really isn't helpful. It's helpful, very, very helpful, but you just can't use 1 to find the GCD of two numbers. What we're really using is 2 and 3, and that only works some of the times. But in our level of classes, many times one of the two will work, and that's the reason I've given them to you. Other times we have to find it another way, and I'm going to show you that way. It's called my table method, and we'll be using it as appropriate. So let me get my writing, my blue board, my blackboard up here. So let's look at the GCD of 4 and 28. So what do I know? I know that whatever the value, so this is some value, right? Whatever the value is, it's greater than or equal to 1, but it's less than or equal to 4. So right off the bat. But notice that 28, which is the larger of the two numbers, divided by 4 is equal to 7. So the smaller of the two numbers evenly divides the larger of the two. So that tells us that the GCD of 4 and 28 is actually, in this case, equal to 4. So we used rule number 2 for that one. Now let's look and find the GCD of 3 and 9. Now notice that 3 is a prime. So again, I always know that it's greater than 1 or less than or equal to 3. Now 3 is a prime, but notice that rule number 2 applies in this case, because 9 divided by 3 is 3. So 3, the smaller of the two, is 3, evenly divides the larger of the two. So in this case, the GCD, we're using rule number 2 again, of 3 and 9 is actually equal to 3. That's as large as it can possibly be. Now let's look at the GCD of 11 and 26. And recall, 11 is prime. It's on that list. So again, I always know it's greater than or equal to 1 or less than or equal to 11. But in this case, 26 divided by 11 is not, it doesn't evenly divide it. There's a remainder. Has a remainder of 4, actually. Remainder upon division is equal to 4. It needs to have a 0 remainder. So condition 2 doesn't hold. So I can use the rule 3. Since 11 is prime, in this case, the GCD of 11 and 26 is equal to 1. That's the smallest value it can take. And now we get to our first different type of approach. So let's find the GCD of 6 and 21. Now neither 6 or 21 is prime. I just put that down there. You don't have to do this step. It's just to remind you that whatever the value is, it's going to be greater than 1 or less than or equal to 6. So we have to find some way to figure out the GCD of these two. Because 6 does not evenly divide 21, so I can't use rule 2. So here's what we do is we make factor trees. So, and we're going to make a table. So I'm going to make factor trees of 6 and 21. So 6 is even, so if something's even, it can always be divided by 2. So 6 divided by 2 is equal to 3. And both 2 and 3 are prime. So as soon as you get to the end, the branches, or if you want to call them the roots of the tree, and you have a prime number, that's where it stops. Now over here for 21, 21's not even, but you know 21 is divisible by 3, and 21 divided by 3 is equal to 7. So again, 3 and 7 are both prime, and I stop. So now I make a table. So my table is going to have 3 columns. The first column is going to be for all of my different prime factors. So however many different prime factors is how many rows you have to make. And then I will have the first number 6 and second number 21. So here are my prime factors. So how many distinct prime factors do I have? Well, 2 occurs just once. There's a 3. And it doesn't matter that I have a 3 here and a 3 here. I'm just looking at the different prime factors. And then I have a 7. And now what you do is this. You look at 6 and you ask yourself, how many 2's occur in the prime factorization of 6? Just 1. How many 3's occur in the prime factorization of 6? 1. How many 7's occur in the prime factorization of 7? 0. Over here, now let's go to 21. How many 2's occur in the prime factorization of 21? Well, 0. How many 3's? 1. And how many 7's? 1. So here's the formula. We're going to extract this information to find the GCD of 6 and 21. It's going to be equal to each of the prime numbers raised to some power. And recall over here that any number b, as long as b is not equal to 0, then b to the 0th power is equal to 1. So we're going to use that fact right there. If b is not equal to 0, then b raised to the 0th power is equal to 1 for any number b. So what I have to do is find the exponents of these 3 prime factors. So what I do is I choose, look at each row, and choose the smallest value. You might have been thinking the largest value because it's the greatest common factor. But no, we choose the smallest value in each row. So the smallest value in the row for the 2's is 0. So that's the power I put on 2. The smallest value in the row for 3 is 1. So that has a power of 1. And the smallest value in the row for 7 is 0. So the greatest common factor of 6 and 21, well, 2 to the 0th is 1. 3 to the first power is 3. And 7 to the 0th power is 1. So that is equal to 1 times 3 times 1 is just equal to 3. So the GCD of 6 and 21 is equal to 3. And we already knew that it was going to be less than or equal to 6 and greater than or equal to 1. And indeed, it's equal to 3. So let's use the same method to find the GCD of 12 and 36. So what I'm going to do is the factor trees for 12 and for 36. So you just start. It doesn't really matter where you start, but if they're even, I like to start dividing by 2. So 12 divided by 2 is 6. 6 is even, so it can be divided by 2, and 6 divided by 2 is 3. So that's it. Those are my prime factors. I circle them. You don't have to circle them, but I'm going to. And then 36 divided by 2 is 8. Sorry. Supposed to write 2 is 18. And 18 divided by 2 is 9. Now 9's not even anymore, so I have to think of another prime divisor. And 9 divided by 3 is 3. Now if you'll observe, all of these numbers are primes. So I have a lot of 2's and a lot of 3's. So when I make my table, I only have 2 different, in all of that list there, I only have 2 different prime factors. So again, we have prime factors and they are 2 and 3. It doesn't make any difference. It doesn't make at this point the fact that we have 1, 2, 3, 4, we have more than one. I just want different prime factors. Then I put 12 here and 36 here. Now starting with the 12, how many factors of 2 do we have in 12? Well, here's 1 and here's another, so I have 2. How many factors of 3 do I have in 12? Well, I just have that 1. Now, looking at 36, going down, how many factors of 2 do we have in 36? Well, I have 1 and 2. How many factors of 3 do I have in 36? I have 1 and 2. So my GCD of 12 and 36 is going to be equal to 2 raised to some power times 3 raised to some power. So what do? We find the smallest number in each of the rows. So for the 2 row, my circled number is 2, so it's 2 raised to the second power, and then 3 raised to the first power. So that's equal to 4 times 3, which is equal to 12. Now I know if I had been alert, I could have used rule number 2 to actually discover this, because 12 evenly divides 36. But I wanted to show you that this method works. Even if you forget those rules, this method will always work. You can just throw those rules out. But how much nicer would it have been if I would have noticed that, oh, well, the GCD of 12 and 36 is less than or equal to 12, but greater than 1. But 12 divides 36, so it's equal to 12. So that's really fast. But I did it this way so we could actually see that this method works, the table method works no matter. And our last one. Now notice here, and I did this quite on purpose, that there's no sorry for the delay when you record at home. Sometimes the phone rings and you have to stop what we're doing. So we were to find the GCD of 1848 and 220. Now notice that the 220, the smaller of the two, comes second. It doesn't matter. There is no real convention. But I know whatever the number is, it's less than or equal to 220, but greater than or equal to 1. So since 220 doesn't divide 1848, I can't use rule number 2, and neither of these numbers are prime because they're both divisible by 2. So I have no choice but to do my factor tree and find the factors. So 1848, it's even, so I'm going to divide it by 2. And when I divide it by 2, I get 924. Again, 924 ends in an even number, so I can divide it by 2. And when I divide it by 2, I get 462. Now when I divide 462 divided by 2, I get 231. Now it's not obvious what I should try to divide it for, but there's a little trick, and I'm going to remind you. Divisible by 3 test. So what you do, we teach this in developmental math, many of you who have not had that, is you take the digits of your number and you add them together. So 2 plus 3 plus 1 is equal to 6. And is 6 divisible by 3 evenly? Yes. So it means 231 is divisible by 3. And when I divide it by 3, I get 77. Now it's really easy. I know 77 is divisible by 7, and 7 times 11 is 77. So there are all of my prime factors in 1,848. 222 is going to be much easier. Now I don't have to divide this by 2. I immediately know it's divisible by 10, right? And 10 times 22 is equal to 220. And 10 is divisible by 2 times 5, and 22 is divisible by 2 and 11. So in the end result, I still get the end of my roots or the end of my branches prime numbers. So let's take account of how many different primes I have. Well, I have a 2, I have a 3, I have a 7. These don't have to be in order from smallest to largest at all. I already have 2 in my list. Oh, I don't have 5 in my list, but I have 11. So there I can easily make my table. Now this table is actually, we do more work than we have to, but it's an easy way to see things. And by doing this table in other classes, we can also find the LCD. So these are, these are my prime factors. So now I put 1848 here and 220 here. And I know that the GCD, I don't want to use that, but rather this. See if it will work now. The GCD of 1848 and 220 is going to be equal to 2 raised to some power times 3 raised to some power times 7 raised to some power times 11 raised to some power times 5 raised to some power, keeping in mind that power may be 0. And remember, if it is 0, then really the factor just drops out because any number raised to the 0th is 1. So let's fill in our table. 1848. How many 2's do we have? There's 1, 2, 3. We have 3 2's. How many 3's do we have? Well, we have 1. How many 7's? We have 1. How many 11's? We have 1. And 0 5's. Now, as soon as I have a 0 there, I'm done with it. I really don't have to carry on, because 5, the smallest, we're going to be choosing the smallest numbers in each of these rows, so I immediately know that's going to be 5 to the 0th, which is equal to 1. So over here, 220, how many 2's do I have? I have 1. I have 2 2's. How many 3's do I have? 0. So I found a 0, so I know that's going to be, there is nothing in here can get less than 0, and I'm always going to choose the smallest of the values, so that's gone too. How many 7s do I have? I have 0. So that means that's going to be 7 to the 0. So those just become 1s. How many 11s do I have? I have 1 11 and I have 1 5. So now we find the smallest of our numbers. So we have 2 and 1. So as it turns out, I've already got it here. Everything's been eliminated. It's equal to 2 raised to the 2 power times 11, which is equal to 4 times 11, which is 44. So the GCD of 1,848 and 220 is 44. That's our final answer. And we can actually check that 1848 is divisible by 44, and that 220 is also divisible evenly by 44, and that's the largest number that evenly divides both of them. So I hope that helps. We'll be revisiting the GCD later on, and the really nice thing about this table is there's a cousin to the GCD called the LCD or the LCM. And literally, given a table like this, I can use the exact same construction to find the LCM of two numbers. But that's a different lecture for a different time.